Good afternoon. This is Mark Richardson, Marketing Manager with Vibrant Technology, and I welcome you all to another MEscope webinar. And this month, we are going to look at modal analysis with a high-speed video. And again, I'm, as always, joined by our partner, Dan Ambray with Full Spectrum Diagnostics. And we'll get going here in a minute. Before that, just want to remind everybody, everybody's going to be on mute for the duration of the webinar. If you have questions, go ahead and type those questions in the questions box there in the GoToWebinar panel on the right side of your screen. And we'll try and get to as many questions at the tail end of the webinar as possible. And wanted to also remind you that this webinar is being recorded. So at the completion of the webinar, you will get a link to the entire webinar. So if you missed anything or you want to go back and review something, you will have that capability as well. So with that, let me hand things over to Dan and we will get going.
Good afternoon, everyone. Thank you for coming to another webinar for the MEscope ODS videos. We have a new aspect of it this week. We're trying to do modal analysis with the video. And it's basically set up for operating deflection shape, but there shouldn't be any reason why we can't do modal. My first try at it, I'm going to bring up MEscope. Where is it? Come on. Why didn't that work? Oh, because I'm on the wrong peak. I'm in the time waveform. Sorry about that. Okay, so what you're seeing on the screen is a beam, my modal beam, and this is my and do a job where I'm going to use the hammers and the make sure everything works right before I get on the job. So I hit this plate and it rings at certain frequencies, and we're seeing exactly what we're looking for here. So I hit it, and let me first go back into the time waveform so you can watch me hit it. So nothing's going on here, and I think about a couple seconds it'll show up. There's my hammer, and I hit it, and you'll notice I hit it pretty hard. So it bounced. It's on little foam pieces on either side of the plate under here, so it's made to bounce. But the way you do modal testing, you don't hit it hard enough that the hammer stays on the structure for more than just a bounce. If you do, then you start double hitting and you get some corrupted data. And in my case, I lost one of my modes. It's around 100 hertz, but it's in the noise floor, so I couldn't find it. But I did find, if I go to my frequency spectrum, there's my bounce mode when I hit the structure. So I hit it off center, and it's pitching and bouncing. So there's really two modes embedded in there. Here's my second bending mode. And remember, my first bending mode's right around 100 hertz, and I couldn't find it for the life of me. And this is third bending mode. So it works. It is a little finicky. It's not straightforward, but it like anything, the video analysis, it gets you into tough spots where you can't actually put transducers on equipment. And one of the things that I worked on this week, I'll show you in a minute, but it turned out to be kind of an inaccessible thing. It was built for ODS videos because I could never possibly take measurements on it all. But in the video, 5 minutes of video and I'm ready to go. I have a nice modal analysis of the structure. So let me get into that. So I'm in my PowerPoint presentation here. And here we go. This is a carport in a parking lot of a big box store where you pull in if you order groceries or something. You can pull in here and they'll bring them out to you and keep you out of the rain. So it's a frame structure. There's some nonlinearity. We're going to talk about that in a minute. But there's some do's and don'ts about doing something like this. I had to go to this place 3 times and take video 3 different times because I didn't think about some of the stuff that I'd be facing. I thought, oh, this will work. And I walked in and expected everything to be fat, dumb, and happy, and it wasn't. So I had to do a couple of iterations. One of which, I'm using the 1.4 Cronus camera. This is my sledgehammer. So it's an 8-pound sledge that I just bought at Lowe's. Put some rubber on the end of it, so when I hit structures, I don't hit them, you know, too sharply and cause a lot of high frequency noise. And I was using this to excite the structure. It doesn't need to be, you know, coupled to the camera as a trigger because video is simultaneous. So everything in every pixel's a time waveform, and they're all synced. So it's made for doing modal analysis and operating deflection shape. So you just have to have the right applications. This is the shot I'm going to get. If you can see up here in the upper right, that's a tree, and that's a bunch of leaves. And this is a windy day. And there was my first problem. Okay, so some pitfalls, and we'll get to that in a second. Secondly, it's a cloudy day, and the clouds are moving because it's windy. So that is a lot of background noise, low frequency, high amplitude background noise, trees and clouds and so forth. So I couldn't get the entire structure that I wanted, and I'd be standing out in the middle of the parking lot, and I think people get a little upset. So my focus was in this block area right here. So I get these 2 truss structures or 3 truss structures out of the 4, and I can see how they're moving. Now, one thing that's interesting, if I was doing an actual job on this and somebody asked me, hey, can you take some vibration data on this structure, I could do it. It would take a little effort. But what I would rather do is do a quick video and get my rigid body modes, and then I could make a finite element model and I could correlate the model and it would be easy. There are a couple other pitfalls. This is a nonlinear structure. There's cables that run along the canvas. The canvas moves independently of the frame. There's some pin joints. These longitudinal trusses have pin joints in between each of these arcs. So there's 4 different arcs, and you have little pieces of that are pinned together. And it's not a good, and when I say nonlinear, if I hit the structure like I did right here, energy has to go through the entire structure, which means it's going through some pin joints and it's losing some of that. So it makes having a linear mode shape a little bit of a problem. Not for the rigid body modes, but for mostly for the bending modes and things like that that are independent. Okay, so my description of this is a semi-rigid truss structure for grocery pickup at a big box store. Requirements, modal analysis requires a linear structure. We're going to do this anyway. It's big, it's kind of inaccessible. I actually had some employees of the store come out and give me a hard time, try to figure out what I was doing, and I got through that successfully, but there's some requirements there. Hammer, 8-pound sledge with a rubber tip. What I need is a single impact in an 8-second period. If you remember, the Cronus camera has an 8-second buffer, so I have to hit the start button, go out there, hit the structure, and get back to the camera in 8 seconds to turn it off. So per shot. It also requires a lot of thought about what directions and how many measurements and how to break this thing up. And my logistics in this parking lot were cars going constantly, so I was a little limited there. Now the pitfalls, multiple camera positions to interpret the response, that was key, because X and Y is trying to mimic a 3-dimensional mode shape is a little difficult with a camera and XY display, but with different directions, it's great. Pitfalls, clouds in the background, I mentioned, trees and bushes blowing in the wind. I had pedestrians in the background walking by. There was a fantastic brake smoking area right by the kayak there next to the wall. Cars were driving past in the background, and keeping myself out of the camera video took a little thought. If I took this whole frame, I'm hitting it at this truss right here. I had to make sure I was out of the camera range. Now, why is that? Because if I walk through, I'm a low frequency, very large amplitude event, and that will cause all the random noise in the spectrum and waveform that aren't really there. Okay, they aren't related to the truss structure. So now I can swamp the data, the lower amplitude data that's in the truss that I'm trying to find. Just like that first bending mode, I couldn't find it because hit it too hard. Very likely my hand was in the way and caused a big amount of response, but you know, a lot of pitfalls, but living is learning. Remember last webinar in January, we had something called a deflection relative to points command in the tools, not in the wizard itself in the software, but the tools. And the algorithm is designed to remove camera motions due to camera starts and stop transients, sensitive tripod mounts, flexible plating or grating that your camera's on, mezzanines, platforms, all that stuff, windy conditions, and all the pitfalls from the other side. This actually worked unbelievably well, and I'm going to show you how that works in a minute again. The idea is to select the background grid points that are moving due to camera motion. The motions are averaged and set to 0, so all the background goes completely to 0, but the average amount of vibration that we found in the background, that's subtracted from the remaining grid points. So we get a new time waveform and a new frequency data block that's created to get the real relative motions. This is one of the impacts in the time waveform, and I thought it'd be interesting to see. As you know, every pixel is captured simultaneously. The time waveform impulse is calculated for each one of those pixels, so we get a pure ring down. We don't need a reference since everything's synced together in the time waveform. And when we do an FFT, we retain the phase response from the waveform as well. So this is typically what we're doing, and I took a few measurements so you can see what this wiggle is in the time waveform. Okay, and it looks pretty good. There's a little background noise that I didn't get rid of, but you can do that too. You can put the deflection to a point in there and get rid of it. Modal analysis has data that usually needs to be curve fit. Okay, my little plate that I showed you, second bending, third bending, rigid body modes, all that stuff, I never curve fit, but this truss structure I did. And the idea here is to make sure that you're actually zeroing in on mode shapes instead of something that's not. It's an amplitude, it's background noise, it's what have you. So there's a quick fit option in the software for curve fitting. Initiates modal indicator. So first of all, it asks you what do you want to look at, the real, imaginary, or magnitude response in your quick fit. And if you guys haven't had any curve fitting experience or modal analysis experience, this step is very easy because it's all within the quick fit option. So you say, hey, quick fit the data, and it does it. Okay. Down at the bottom here is the modal indicator, and you know you can use real, imaginary, or magnitude. I use imaginary, which is typical. Defines the frequency and damping for each mode, so it's going to find a peak for each mode. All the ones that I have a little blue cursor on and that one red one there, so there's 10 modes that I looked at, and it gives me frequency, damping, what units we're in, percent damping. And it was helpful. I have some unstable modes in here. So this number 2, either there's too much background noise or it's not really a mode, or it's buried in, you know, just like my plate mode, it might be buried in noise. So we'll get an idea from that, what's going on. Okay, and then I can curve fit and do all those and create a shape table and animate from that. But the idea, it's very quick. Okay, you don't have to know anything about curve fitting. It's a 5-minute tutorial and you'd be up and running. Okay, and get your good modal results. This is a set of data that I took, in roughly the same angle that I showed you. And I left all the points on. And the black points, or all the beams and the canvas and everything in here, those are the stuff I wanted to retain. I wanted to get rid of this tree and that tree and all this background, and there's a street where cars are going by and so forth. These are all the red points that I selected to, group select pretty quick. Takes a couple minutes to put them all in and, get it all the way you want it. But it removes all that background noise, and actually just looking at the points and the way the points are moving, it's almost like a vector plot. So you can see how everything's shifting for the mode shape. And I got a kind of a rigid body pitching motion in here. If I remove those point or not the labels, but the actual points, they all go away. The background is solid. Oops, there we go. Background doesn't move, and my structure does. Okay, another thing I was looking at for this low frequency mode, this is 21.7 CPM, very low, is the color contour. And you get an idea from this if everything's moving together or not. And it appears that it is. So the only thing moving that I hit was the frame structure and the canvas. All the wind effect is taken away, all the clouds, anything like that. Any background noise or camera jitter is removed. This is another frequency, 102.3. Get this guy started. And again, I left the dots on so you could see a little bit how that looks. And they're kind of moving out of order. Remember, this is a pin structure as well. So the frame itself, it's all moving together, which is a good rigid body type mode. And I can't tell from just this one view if I have in and out of the plane motion. All I can tell is X horizontal and Y vertical. So I do need another direction, and I did a couple of those. I couldn't get the whole thing in my frame, but I did get one of these struts to show the lateral or the longitudinal motion instead of the lateral. And here it is without the points. And there is some distortion in these rounded areas and even up here in the structure because of eliminating those points of background noise is a little more difficult, and the canvas is moving independently of the frame in some areas. But if you look at it long enough, you can see how it's pitching side to side, and there's a little bit of a twist to it, and in the other direction it is twisting a little bit from section to section. Here's my color contour plot, and it's all green's not moving too much, red is quite a bit, so you have little hot spots, but the whole structure's moving as a rigid body for the most part. The last one, mode number 3, is at 209 CPM. I'll get him going. And I am in this XY plane, so it appears that, hey, all these modes look the same. Well, this one is completely different from the other two. One of them's a rigid, this one has bending in it and pitching. And you're gonna have so many different modes from this because there are 4 different truss structures, and they're pinned together with each one of them. So you're gonna get multiple modes for each and then together, and it gets a little overwhelming. And like I mentioned before, if I was doing an analysis like this, it would be a lot easier just to use MEscope to make a finite element model because all the physical structures are pretty simple, and get it all pinned together and what have you. And I have those rigid body modes, so it should tell me where all the other modes would be, and they'd be pretty accurate. I'm going to go to the next one. So I've removed the points. It's supposed to auto start. It's not. There we go. So you can see that pitching motion, which is super interesting. I saw my first one that I tried and it was moving like this. I'm like, oh, this is fantastic. So I have a lot more ideas about tower structures and buildings and frames and all kinds of things I can use this for. And here's my color contour, and this one's a little different. This one, the frame is moving a little bit more than the canvas on top. And maybe it's a sliding thing or what have you, or maybe it's just out of plane and the canvas is moving in the other direction. I don't know. So the couple of interesting things, I've been trying to figure out how to display things to get a better look at them. And this one, I left the points on that I removed and the points that I've saved, but you can see how the overall motion is. Another thing here to look for, and I never even thought of this till about an hour ago, down here where the shadow is, or where the sun and the shadow meet, across that line, the pixels changing color or changing intensity quite a bit. So as there's a little bit of vibration where those moving in and out of the sunlight, the pixels on the boundary there, you get a pretty big looking vibration. This is not it's just distortion. It's not really bending that much right there. This thing was into the concrete, and I'm sure it was pretty deep into the concrete. So there is some bending going on, some twisting, but not as drastic as that. That's kind of amplified in the animation. And here it is without the dots used for reference. And you can see all three beams are flexing. And it's, this frames, the beams are off center with respect to the carport structure. It's larger on the outboard side here. So you would expect a bending mode and twisting in this structure here. And I have the capability to put points and lines and things like that on the structure. So I just did a real quick series of lines on the trusses just to see what I could see. And this might be an interesting thing to do in the future, at least for me. Gives me a better idea how the global structure is moving. So one truss with respect to the other. And there's a couple of different options in the software. You can normalize the response, especially for modal analysis. If you're sitting right on a natural frequency, it should be normalized. If not, and you're looking for motion like this that's a little out of phase and a little more realistic, you can take the normalization off and look at the mode in a complex view. So whatever you recorded it in will show you how it looks. But I do like this. I mean, it's pretty crude that I drew these lines in here, but it does give you a different perspective on how it's moving. And it's underutilized, I'm sure. And the last one is the color contour view, and the whole frame is basically moving. Sorry about that. The whole frame is moving, and you can see how it's flexing in here in the middle of each of these beams as it twists. Now I'm going to walk through kind of what we just talked about and just give you a rough idea of how we look at data through the wizard and through the MEscope version of this type of software. When you log into the software and start up MEscope, you have a home panel where you have videos, and you can either reprocess a video or use a new video. And we'll go to a new video. and it'll bring up our wizard. And there's a couple things in the wizard that have changed, and we'll get to a couple of those. First thing we're going to do is we're going to open the raw video. So we click on that, and it takes us to wherever we are storing our videos. And here's I have a selection of 4 different truss structures that I can pick, and I pick this one down here and hit open, and it brings it into our wizard. Okay, a couple of things that if you've seen this before, we can rotate this. We can take a video with the camera in the horizontal direction or the vertical direction, and this will always drop the camera in horizontally like a landscape. So we can turn that 90 degrees if we have to. Okay, and we can get the frame oriented right so it doesn't drive us crazy. We can also play with the brightness and contrast, and being outside, I know I do most of my work inside in power plants and such that are much darker. Here you don't even need lights, everything is nice and clear. The only thing, I keep saying this, trees, clouds, they are not our friends. They make things very confusing. So you're going to have to use the deflection from a point command to get rid of some of that background noise, or all of the background noise. Okay, so we set the brightness, contrast. We can crop the video a little bit. We can rotate it, and those are all our adjustments. Our frames and duration, step number 2, we have to tell the software our frame rate. So this is 1057 frames per second. That just tells us what our maximum frequency range is. And if this is our frame rate, half of that is our F max, basically. So 529 hertz, something like that, cycles per second. In this video, there's some low frequency stuff. I'm going out and I'm actually hitting the structure and triggering the vibration. So I have to have a nice chunk of time, and the buffer is 8 seconds long. So I am processing the entire 8 seconds, which might take a few minutes to do. Excuse me. But anyway, I just want to unload the entire buffer so I can see the impact, I can see the ring down, and I can always clip it out afterwards if there's something in there that I don't need. Anything else? No. We go to next, and we go scaling distance. This is a known dimension on my video, so I don't have to range my camera to the structure. I can tell the video that this is 12 inches, and it'll scale appropriately, and I will have, you know, dimensions that are very close to being perfect. So I set the distance, and then I can set the number of points. And this is a very fine mesh. And we should remember what this is. This is not the pixels, but a representation, a much coarser view of all the pixels on the screen. So we're looking at 12,672 measurement points. And that sounds really small when you think that my resolution would give me 1.3 million pixels. But if I tried to process, you know, in the same way, 1.3 million pixels, it would take a very long time to process any data. In this case, the 12,000, that's pretty high. I don't usually go this high to be able to represent anything. But a couple of my trials this week were trying to turn on and off points close to curved surfaces. And this structure is lots of curved surfaces. So needed a little more resolution so I could pull off, and it would look really good instead of choppy. So that's what I did. So the number of points, we extract the time waveforms, and it'll pull a waveform for every point and tell us how it's moving. I can take away some background noise with this command, with the filter displacements. It's low frequency, high amplitude response on that side, and then high frequency, low amplitude response on that side. I'm going to use the deflection by a point because it works better for both of these conditions. So I didn't really use this for this case. And usually I don't, if I have to reprocess and I think it might be helpful, I'll do it then. Point graphics is next, and since I had so much resolution, such a fine mesh here, I can barely see anything. Here's one of my structures and the arms on it, but it's very difficult to see. This is used to put in labels, put in mag and phase values. I can have orbits around all the points. I can have vectors. So I can select particular points, and I did it a couple of times, just trying to see the vector plot, but it wasn't as clean. It looked a lot more like the point plot that I had up before. There's just too fine of a grid for it to be real useful. So I hit finish, and I have an example here of the camera jitter. This was me turning on the camera. Okay, there's a pulse, and that was part of the waveform, but it showed up, obviously on every waveform. You can get different types of pulsing and jitter in the camera from the start-stop transients like this, sensitive mounts, flexible plating or grating that the camera's sitting on, mezzanines, platforms, all that. But this was a good example of just touching the camera. It's very sensitive. Usually what I tried to do is let it fill the buffer, and I can turn it on and then count to 8 or 16 seconds, and then I know that any transit's been flushed out of that 8-second buffer. And again, deflection relative to points, that's all the red dots in here. We select the background points highlighted in red. The background motion, the XY directions is averaged and set to 0. The averaged background motion is subtracted from the unselected points, and new time waveform blocks and frequency blocks are calculated. So we permanently get rid of that background noise, and then we can play with the images and see what we can find. As we've talked about a couple of times before, this is the vibration fault periodic table. It's a logical visual mapping system to understanding vibration. You might not be a completely expert in vibration analysis, but it gives you a roadmap to follow. So it's grouped by frequency groupings: synchronous, harmonic, subsynchronous, non-synchronous, and modulation. These are our frequency groupings here. So there's 5 of those. It's also grouped by dominant response direction. So the red is radial, the yellow is axial, the orange can be radial or axial. Okay, so if we do initial sorting is by frequency range. If it's I have high vibration at turning speed of the shaft, then it's a synchronous problem. If I have high vibration at some multiple of turning speed, it might be 32 teeth on a gear, 6 blades on a pump, 49 rotor bars in a motor. They're exactly 36, 6, and 49 times running speed, exact multiples. Subsynchronous events are things that occur below running speed, less than 1 times RPM. Non-synchronous are just the opposite of harmonics. Harmonics are exact multiples. Non-synchronous response is not exact multiples of running speed. And modulation or beat frequency type faults are over here. Okay, so we can sort it by frequency, we can sort it by direction, and then we're left with, instead of 35 different faults like we see on the table, it'll go down to 11, it'll go down to 4, and then inside each block is what we do next. So this is my unbalanced block. It's red because it presents itself in radial directions. And it has a little phase icon in here. So it's telling me what to do next. Once I've sorted with respect to frequency content and direction, the block itself is saying you need to do a phase test now. If you'll notice, the first 2 columns on the table, with the exception of this gear problem, are all phase analysis. And using the MEscope software, operating deflection shape, it's all about phase. Modal analysis, it's all about phase. So any project that you do, you might be able to solve it based on this table. It might be something else, a bearing defect or what have you, but something else is causing it. And these first two columns are key to understanding anything. And if you want to, you know, go in and do a phase analysis, you're checking all the different things across the coupling misalignment, cocked bearings, mechanical looseness, bent shafts, belt drive misalignment, unbalance, eccentricity. Everything that's phase related is right there, and then natural frequencies as well. Okay, so my 5 different tests are: you do a time waveform, a phase analysis, an orbit analysis, some transient analysis, or ultrasonic analysis. So what I just explained to you is something that you can follow. Okay, you might not know how to do a time waveform or a phase analysis. You don't know what a spectrum is, but you get the idea. It's a frequency group, direction, and then do a diagnostic to sort it all out. Okay, and MEscope is built for that: modal analysis and operating deflection shape. And here's the faults that stick out for doing ODS and modal. Okay, we've talked about the last few months a lot of these: bent shaft, cock bearings, and what have you. The natural frequencies are over there. So can MEscope ODS videos do modal analysis? Yes. It's and it turns out that it's rooted in massive structures, you know, bigger than, you know, your boiler feed pump in a plant. Big structures you can't take data easily on, like towers and I don't know, cranes and my little carport or what have you, buildings, but you can take video. And one other thing that I was going to put in here is wind turbines. And probably about a year ago, I did a wind turbine project, and we did a webinar on it. That was my first modal analysis because they wanted to know what the natural frequency of the tower is, so that to make sure it wasn't coinciding with the rotational speed of the blades. And what we did was we had the machine running at full tilt, and we did an emergency stop, which is not what you'd think. There's no brake or anything like that. We hit the button, it turned all the blades into the wind, so they lost their lift, and that was a pulse in itself to exciting the natural frequency in the tower. So it can be done, and video is the only way I could do that. Now we got a couple options. There's a couple cameras that are put out by Kronos. There's a 1.4 and a 2.1. I think Mark told me that this was the 1.4 camera, and that's the one I use. It's color and so forth. But this thought process, maybe it'll go through your mind. If you're interested in buying this equipment, that's great. If you want to take it for a test drive, this is the way to do it. You get camera, lights, light stands, tripods, equipment bag, and 30 days worth of the software. And I put together a step-by-step quick start workbook as well, so you can hit the floor running. But $3,075 a month. You need to talk to somebody at sales@vibetech.com, and they'll give you an idea what you need and when it's available. If you think all this is awesome, you have no time to learn, on-site diagnostic options are available. I go around to different plants and I do this type of work. And it can be a learning experience. Plus, take care of one of your problems, one or two, three, or whatever time gets us to do. But usually it's a one-day little thing, and everybody gets to use the camera, and we get a little better feeling, a little more close to the camera. How much does it cost? What do I need? Purchase options are available. Starting from scratch, the full package with the camera, tripod, lights, and software is right around 20,000. Okay, if you already have ODS software, just the basic ODS package, all you need is a signal processing upgrade, and the price goes down to about 15,000. If you have a high-level MEscope software, you don't need this. You only need basically the camera, and you'll be ready to go. A lot of versions available. If you want to talk to the people at Vibrant or go to their website, you'll be able to see everything that's available right now. And that's it for this webinar. I assume there's going to be a few questions.
A couple questions, yeah. If you have questions, go ahead and get those questions typed in, and we can go get those answers right now. I believe you answered this one. First question: how was camera glitter removed? And I believe you had a slide on that one, but maybe you want to just review it real quick.
Removed? Well, it's that
camera. I'm sorry. How was camera jitter, not glitter?
Jitter, yeah. Well, I knew what you meant.
Yes.
Well, the jitter is shaking the entire frame when you think about it that way. So if the entire frame is shaking, the background's shaking, the foreground with the real vibration is also shaking, it dominates everything. So what you do is if you highlight all the points that you want fixed that are in the background so they don't distort your video, you change them from black to red. So basically you select all those background points, and then you punch the command deflections to a point, and it calculates the average background vibration, all those selected points, and then it sets them all to 0, and then it subtracts that background vibration from the unselected points, if that makes sense. So that's the vibration that's on top of what the real vibration is from the jitter. So the jitter's gone, the background's fixed, the motion in your structure is the actual motion of the structure. Hopefully that makes sense.
Next question is, did you set a reference on the ground?
I did not. You don't need it for this type of testing. The hammer's usually a reference. And when you hit the structure, it measures the force going in and the vibration going out, G's per pound, basically. And you get your natural frequencies and so forth, and your mode shapes. You can also do modal analysis where every point is a time waveform. So any point could be the reference. And you have a phase between all the points that's locked in already. So if I go out and do it normally with accelerometers, I hit it with a hammer, take my data, move the transducer, hit it with a hammer, and so forth. You need something that stays put, and hitting with the hammer stays put. When you're doing ODS videos, all the points are being measured simultaneously. So there's your phase.
All right, next question. Can you have a 3 to 4 second delay on camera recording to avoid the shaking when turning on and off?
Yes, actually there's an off. I always talk about starting the camera, and I obviously can't get away with that. It used to be, and I haven't downloaded the latest software from Kronos, but the trigger that they use, you can apply it to the start and the stop. It's basically a USB trigger, that cable that plugs into the camera, and there's just a push button. I use it to shut the camera off. I just haven't got the software yet to use it to start the camera. If you do that, then most of your problems will go away, except for wind and and if you're sitting on a framework or a mezzanine or what have you, there's always vibration on those. But yeah, there's a way to do it. There's a start-stop trigger.
All right. How can I get your quick start workbook?
Well, if you want to rent a camera, that's when you get it. If you want to buy the system, it'll be part of the training. Right now I'm set up to do my normal vibration training. So I teach you about MEscope. There's like 1 day of modal and ODS background information and animations and so forth to get you oriented of what you're looking for, what you're going to see. And then there's a 2-day workbook part of the class where you would go through the software from start to finish. So you basically start out doing real simple things, and then you start building models, and then you get into more complicated models, and then you have data acquisition, and it takes you from crawling to running pretty quick. And the nice thing about having a workbook for that is you can go back to it. So everybody goes back to work and they got other things to do, and you might have this sitting on the shelf for a couple months, and then you want to use it, you pull out the workbook and you go through it and do a couple of the examples and get your confidence back, and that's the way it's going. For the ODS videos, if you just wanted training on the ODS videos, then there's a similar workbook that kind of lays out the logistics. How do you want to take your data? What's your goals? How many different directions you need? How many close-ups? And it's from machine to machine. And like somebody just asked, was there a reference? Whenever I do the regular ODS with the camera, I put a transducer in the frame. So I can use it for both the distance, the set distance command. It's like 1 3/8 inches per square, the transducers that I use, the CTC ones. And also I can take a physical measurement there to compare my video with. So a lot of different logistics and understanding of the camera and how we're going to use it, and obviously the software if I want to familiarize myself with the integration and differentiation, the filtering, the time waveform, the spectrum, curve fitting, what have you. So there's a lot of stuff in the class, and you can pick what you want actually. I think it'll be a 1-day class for the video. It'll be a 1-day lecture for the other class and a 2-day workbook for the other class. And the nice thing with the video stuff, we'll do some in the class. I do it basically on site because that's where the machinery is, that's where the problems are. So we'll learn enough to be dangerous. We'll go out, we'll take some data on a machine or two and make all our mistakes right there. Okay, because everybody big steep learning curve, everybody's going to learn how to make mistakes, and recognizing that you're making a mistake is the thing you really want to do. Like I mentioned, I went out to this carport 3 times this week because I made mistakes, and I ended up fixing it. It was a little more painful, but now I know what to look for different things.
Okay, next question. How do you measure the input force for FRF?
You don't, not with the video camera. It's basically an ODS FRF. You can curve fit the modal data. If you had a hammer, that would be your reference. You measure the force going in pounds. You measure the response in G's per pound, so you have that reference and roving aspect of it. For the video, it's all time waveform, and they're all time synced together. Everything's occurring simultaneously, so we don't have to have a trigger for that or anything, or a reference. And since it is all the phase exists in the time waveforms, when you do a Fourier spectrum, you retain that phase. So you can see how one point's moving with respect to another at any frequency you're interested in.
Alrighty. What's the spatial vibration resolution necessary for success?
Spatial resolution?
Spatial vibration resolution necessary for success.
I don't know. I use the maximum resolution I can get on the camera. So, the cameras are made for high-speed photography. So obviously 1,000 frames per second is fast. These cameras can go up to 35, 40,000 frames per second. So you could watch a gun, a bullet come out of a gun in slow motion if you wanted to. But you can't get as much resolution at 40,000 frames per second. So the maximum resolution is 1280 by 1040, something like that. And at that resolution, the acquisition rate is 1,058 frames per second.
There's
So
a follow-up. Ruben just clarified. Question was meant to ask how much vibration amplitude is needed for success.
needed, it can detect down to like 10 thousandths of an inch.
Mm-hmm.
I mean, it's so 0.0001. I've seen it measure that. And if I want to,
Okay.
I don't know what
have you used.
That's displacement.
Yeah.
Yeah.
Have you used shaker excitation successfully with video?
No, but that would be pretty interesting. I used to do that all the time. I worked for Pratt & Whitney and Sunstrand Corporation, and they had avionics for aircraft, and we'd put them on shaker tables and, you know, acceleration life testing. And I think now it would be fantastic to see a video of what we were doing. And the technology's here now.
We just may have found our next webinar topic.
Yeah, you want to buy me a shaker? That'd be
Find
great.
a shaker table. Exactly. Another question here. How does the process obtain vibration of points in the middle of a uniform intensity area? No light gradient.
No light gradient. I don't understand. Vibration at a point is designed.
Of points in the middle of a uniform intensity area. Maybe I'm thinking like your plate. I guess if you were doing something on, if you're videoing the top, how is it gonna?
Oh, well, yeah.
If there's no light, yeah.
If I took my plate and turned it on its side, I would just have a shiny uniform surface, and it wouldn't matter if my points were there or not. Mm-hmm. What really matters in this shot is what's the edge doing. And, you know, that's the only way you can see what the mode shape is. From the top, or even, you know, at an oblique angle at a 45 here, it's difficult to see what the plate's doing. But that's different from deflection at a point.
Mm-hmm. Okay, here's the $1 million question here. Would you recommend it over traditional ODS? Of course, if the frequencies of interest are in range of both methods.
One doesn't replace the other. There's two things to think about. Video has its place for, you know, large structures, inaccessible things, hot, you know, live steam, you know, all the bad things you can think of. The video is hands off, and you can see things that you would never be able to see, you know, and you can't go and put the transducers in. Like in a couple of weeks, I'm going to do a generator collector ring. So the exciter on the end of a generator, it's high voltage. I don't want to be anywhere near that. That terrifies me. But I can bring the camera and I can shoot, you know, anything I want, and it's hands off, and gives you beautiful results. There are limits to the direction because I'm always creating a two-dimensional video of a three-dimensional object. So I have to, maybe not simultaneously, but I need a couple angles that I can see all that I want to see. And you know, in tight quarters, you can't really do that. Accelerometers are just easy, you know. You map out a structure, you take a bunch of measurements, and it's a fairly simple process. And I don't know. You get rid of that two-dimensional effect. You're always in 3 dimensions.
Here's another good question from David. Have you ever verified the accuracy of this method with using accelerometers on a small structure?
Yeah.
We actually have a webinar.
This plate, these peak, the second bending and third bending, are right where they should be. That's why I chose this. So I could, it's my sanity check. Okay. Like I mentioned, I hit it with a hammer, ring it like a bell, and the ringing are the frequencies that are going into these mode shapes, and I can tell right away if I'm doing something wrong.
And I believe we have on our website, if we did a webinar where and it's been a few months now, and correct me if I'm wrong, Dan, didn't we do that exact same thing where we compared video with accelerometer data?
Well, just amplitude wise, yeah.
Mm-hmm.
And I mentioned earlier that I usually have, like if I'm doing an ODS of this, I would have a transducer on it to verify what I'm seeing, but also as a distance deal. So I could put in the video, I could select a point here and a point on the transducer and match them up and see how accurate we are. And they are very accurate. There's some motor demonstrators that Dr. Mark Richardson did some work on, and the accelerometers are showing exactly what the surface of the structure was showing.
Okay, another question here. Do I understand correctly that the video modal extraction is based on OMA and not EMA?
That's correct, because the force isn't measured directly. So it's basically an ODS FRF. You can start out with the time waveform or the impulse response and curve fit that. It's just another technique.
Another one here, would it help to your modal analysis video to use a stroboscope lamp?
So I could see this bending plate wiggle. It would be too short. You'd have to tune the strobe light and all that. Well, you know, if you do this, if I go back to the time waveform and you watch this thing when it gets hit, this is what you're seeing, all the modes at once. So it's too short. You can't see, you know, the second, third bending mode unless you actually capture data with accelerometers or with the video. But you see there the twisting, the bouncing, that's this low frequency, and then you can't even see these two high frequency ones. The amplitudes are too small.
Another question, is it possible to compensate additional vibration from environment?
Compensate additional vibration from environment. I don't know how to answer that.
Okay. Oh, we got a comment from the Mark Senior here. When the force is not measured, you assume that its spectrum is flat. So the FFT of the impulse response is the FRF.
Oh, okay. So there's no roll off.
Assuming
you don't have to worry about
flat force spectrum is used for all output only measurements, ODF, FRFs, and FRFs.
Yeah, Mark's the brain.
He's jumping in here.
The math wizard.
Let's see. That about answers it. Gary, I will get back to you. Gary Williamson, he was the one who answered about the quick start workbook. Gary actually owns a system, so.
Oh, he does.
Yeah. So Gary, I'll be in touch with you, and we'll get you a workbook there and figure out what you might be needing. If you got any additional questions that we may have not answered, feel free to shoot those off to us. You can send those right to Dan at modalguy@aol.com, or you could send those to sales@vivetech.com. We can answer them here at Vibrant Technology. Appreciate everybody's questions. Oh, one last question. Do you prefer the monochrome or the full color camera? That one just came in. You know, we've looked at both of them.
Yeah, it seems like the monochrome, it shows a brighter response. You open up the aperture and it's a much brighter image. It seems a little less so in the color. You know, I kind of like the color. This, you know, what you're seeing here, it kind of looks blue. This is actually white. It's a function of what light you're using that mute it down. But I think the monochrome does a little better with ambient light.
Great questions, everybody. I appreciate those, and I thank you all for joining us. Again, this is recorded, so if you got any additional questions, if you want to go back and review the webinar, there should be a link in your email box here in a few hours after GoToWebinar processes the video and sends out a recording. We will get another one of these spun up for next month, so stay tuned to your inboxes. And anything else? Any last comments, Dan?
No. Thanks for joining us. And any thoughts? I mean, this one was we put this one on because a lot of people are asking about modal analysis and could we do it? And the answer is yes. You know, there are conditions, but anything else you can think of, anything specific to your own industry too, that, hey, how can I do this? We love answering questions like that.
Yeah, and we'd love to get your feedback on future webinars. If you have some topics you'd like us to cover, feel free to email us, and we will go ahead and try and get that stuff scheduled for you.
Yep.
Okay, let's wrap it up there. Have a great afternoon, everybody, or evening, wherever you may be, and we will talk to you next month. Enjoy your afternoon.